చేసేస్తున్నా మాస్టర్ పిల్లలందరినీ జాయిన్ అవ్వమని ఫస్ట్ దాంట్లో ఫస్ట్ అందరు జాయిన్ అయిపోయి పిల్లలందరినీ జాయిన్ అవ్వమన్నాడు సార్ ఫస్ట్ ఆ గ్రూప్ లో పెట్టిన లింక్ ఆఫ్ చేశాను. అందరు స్టార్ట్ చేసేయండి అందరు ఫస్ట్, తర్వాత మాట్లాడదాం.
Hello, sir. Phanindra, sir. Are you able to hear me, sir?
Hello.
Yes, sir. Yes, sir. Are you able to hear me now, sir? Yes, sir.
Yes, yes, sir.
Yes, sir. Okay, sir. Hi, Dr. Hiromichi. Hi, Dr. Hiromichi.
Hello. Can you hear me?
Yeah. We can hear you. Yeah. We shall start in next 5 minutes. Is that fine with you, right?
Mm-hmm. So starting from
in another 5 minutes. In another 5 minutes.
Okay. Okay. Fine.
Okay. Thank you.
మీ చదువు స్టార్ట్ చేసి
Fanendra sir, shall we start, sir?
yes
Yes, sir. Okay, sir. Good afternoon, everyone. To pre-conference sessions of IEEE Second International Conference on Sustainable Energy and Future Electric Transportation. We'll be beginning our first industrial session. I would like to welcome Dr. Hiromichi Ekimoto. He's the CEO of Albras Technology LLC located in Japan, who is going to deliver a session on floating vertical axis wind turbine for the cost reduction of offshore wind energy. I would like to welcome all the esteemed participants for the pre-conference sessions on the behalf of organizing team of IEEE Second International Conference on Sustainable Energy and Future Electric Transportation, which is technically and financially co-sponsored by IEEE IAS USA, organized by Gokraju Rangaraj Institute of Engineering and Technology, Hyderabad, in hybrid mode. It is a great honor for me to introduce our speaker, Dr. Hiromichi Ekimoto of today's first session, who is going to talk to us about floating vertical axis wind turbine for the cost reduction of offshore wind energy. He is very well known for his work in the field of power and energy domains and renewable energy domains. So Hiromichi Ekimoto, he has completed his PhD in engineering, and he is currently CEO of Albras Technology LLC located in Japan. He worked as a researcher and educator in the field of naval architecture and ocean engineering for 23 years in Japanese and Korean universities. At present, he is developing a new concept of floating vertical axis wind turbine for reducing the cost of energy from offshore wind. He is also developing a low-cost marine current turbine and rotational wave energy converters. Without wasting time, now I would like to hand over this session to Dr. Hiromichi Ekimoto. Over to you, Dr. Hiromichi.
Okay, thank you, Chairman. So I'd like to share my screen.
Yes, please, yeah.
So, hello everyone. Can you see my screen?
Yes, Hiromichi. Yes.
Okay, so my talk is on the floating offshore wind turbine, but it is slightly different from ordinary one. As you can see in this screen, the turbine is vertical axis type and it is tilted. If wind stopped, it will be in the upright position. And then when wind blows in another direction, the turbine will tilt according to the new wind. I'd like to talk why this is good for our for the sustainable future of planet Earth. So, first, this is another introduction of my career. Basically, I was a researcher and university professor of ocean engineering and naval architecture. Presently, I'm working in Albatros technology, and the topics are floating offshore wind turbine, marine current turbine, and wave energy converter. So they are all ocean renewable energy converters, and also working in a kind of high speed, super speed ships. So now we will go to the topic of this floating offshore wind turbine. Background is, first, we have problems, climate crisis. We need SDGs solution. And recently we have international problems, international conflicts in Russia, between Russia and Ukraine. So it will have another energy security problems. We have to provide our energy, especially in Japan. In Japan, we don't have sufficient energy sources, so we have to import oil and gases. But if we can generate electricity from ocean wind, it is good. In many countries, practical offshore wind solution is floating turbine. But actually, at present in Europe, they are conducting development of bottom fixed wind turbines. Foundations are on the seabed, but it is only possible in such a good condition of North Sea around Europe. In most of the environment, seabed is deep, so building a wind turbine on the seabed is not possible. Especially in Japan, we have to develop floating wind turbine. Also, if we have to develop floating wind turbine, another problem is present conventional wind turbine. Horizontal axis wind turbine is expensive if it is floating application. It will be discussed in the later slide. Albatros Technologies proposal is floating offshore wind turbine designed only for floating application. We don't consider any bottom fixed or ground onshore wind turbines. It will be lightweight and simple structure for reducing capital expenditure and maintenance cost. And the turbine design is reusable and recyclable structure. This one is the image of the turbine. Detail will be discussed later because you have to know some background information for understanding this, the merits of this turbine. Roughly, it is vertical axis turbine, and point is this float is rotating. The circular cylindrical float is rotating with the turbine. So the seawater is the bearing support of this rotating device. These are present image of floating offshore wind turbine. they are not fixed to the seabed. Entire system is floating and moored to seabed. There are several kinds of wind turbines. They are usually expensive, but merits are they can utilize deep water region. Deep water region deeper than 60 meters. They will be the region for offshore floating wind turbine. If water depth is less than 60 meters, we can install bottom fixed wind turbines, fixed wind turbines. Usually, a deep water region is far from shore, so the wind there is strong and steady, so they can have higher capacity factor. Capacity factor is the utilization ratio of this system. Usually, a floating offshore wind turbine can have doubled capacity factor. For example, 60%, and capacity factor in bottom fixed wind turbines will be about around 30%. It indicates if the turbine size is the same, floating turbine will produce doubled electricity. Naturally, they have also demerits. It is high cost of floating foundations. It is much expensive than usual bottom fixed foundations. Our concept is vertical axis one, so I have to show these categories. Center one is horizontal axis wind turbine. Most of people think wind turbine is this design. The left one and the right one, these two are vertical axis wind turbine. Rotating axis is in vertical position. The left one is drag type vertical axis wind turbine. This is common, this is popular in small vertical axis wind turbine application in onshore environment. Unfortunately, the left one is not good for large wind turbine application because this one is heavy. It requires much materials to capture wind. So my target is the right one, lift type vertical axis wind turbine. The blade width, the chord lengths of the blades are small in comparison to the turbine diameter. So the materials required for capturing wind energy is small. The proportion of the material is similar to the large horizontal axis wind turbine. So we will consider large wind applications will be horizontal axis one or lift type vertical axis wind turbine. Also, these two wind turbines are quite different shapes. Principal mechanism of aerodynamics are the same. So you can see my cursor. So in horizontal axis wind turbine, if wind comes to the blade and the blade is moving in this direction, relative wind velocity is this one. And its aerodynamic lift force is perpendicular to this relative wind velocity. In this case, this one is this vector. So it will pull the blade to generate electricity. In this case, the blade is in in each blade, you can see the aerodynamic force vector. They will rotate this turbine. Shape is different, but the similar picture will be is possible. If this blade is moving with the rotation of the turbine, relative wind velocity to this blade is in this direction, and the aerodynamic force is this one. So this direction will pull the blade for generating the lift force. So as I said, shapes are quite different, but the principle of the dynamics are the same. So next question will be, is it more efficient or not? Actually, large vertical axis wind turbines are efficient as the horizontal axis wind turbine. But most of engineers will say vertical axis wind turbine is not efficient. It comes from the misunderstanding of this device. Recently, many researchers on vertical axis wind turbines are very small scale. For example, or university researchers, they can use only a small wind turbine model for their academic wind tunnels. Because turbine model is the same, the blades of the turbine is affected by the low Reynolds number condition, higher viscosity effect than the large scale wind turbines. Such difference will reduce the performance of vertical axis wind turbines significantly. And they will write journal papers according to the low efficiency of measured low efficiency. But large turbines are quite different from small ones. Another one is its lightweight structure. This one shows a 5 megawatt case, horizontal axis wind turbine, 5 megawatt rated power. And this is my concept of vertical axis wind turbine. It is also 5 megawatt. So you can see the size is almost the same, but the mass is quite different. In horizontal axis wind turbine, heavy turbine head is on the very rigid tower, steel towers. So tower and turbine, a total mass above the floater system is, in this case, is 700 tons, about 700 tons. But in this design, this part is only 300 tons, less than half of the horizontal axis turbine case. It is because heavy devices are bottom of the turbine. Therefore, this part is quite lightweight. Center shaft is much lighter than the horizontal axis wind turbine tower. So the total cost will be also less than half of the horizontal axis wind turbine case. This will lead to significant cost reduction of ocean's offshore structure. Another point is it has no blade pitch control. Blade pitch control is the mechanism for adjusting the blade angles according to the relative wind. In this turbine case, blade is fixed, and also horizontal axis wind turbine has yaw mechanism that they have to change the direction of the turbine. But such a device, such a mechanism is not required in this case. So the structure mechanism is much simpler than that of horizontal axis wind turbine. And simple is very important in offshore structure because the maintenance cost is very high. This is the power takeoff system of our proposal. As I said, floater is rotating, and weight of the turbine or the entire system is supported by buoyancy. Only the horizontal component of the force is supported by multiple bearing rollers installed around the turbine shaft. Also, we use multiple generators. Generators are installed around the shaft. So shaft can be a sufficient thickness. This design will allow redundancy of the power takeoff system and also cost down of the generator systems. Showing the water tank test will be good for your understanding of this design. I will show three movies. First one is this is in operation in the most severe wave condition. If wave and wind conditions are very high, it will in general, wind turbines will stop rotation. It is called parking condition, and it has survived in the severe tropical storm condition. So I will show the first one in operation. If turbine size, if this turbine is 5 megawatt scale, blade length will be 100 meters. So the present wave coming in this water tank is wave height 8 meters. But this movie is not so interesting because it is very stable. As you can see, although wave is coming, this system is quite stable, or even if floating foundation is small. Next movie is parking condition. So it is in typhoon or cyclone condition. In this situation, turbine will stop electricity generation. So if this turbine is 5 megawatt, now you are seeing the 16-meter wave height waves. So it will happen only in the very large, very strong typhoon or cyclone. So it is also stable. The point is, wave load is around this thin part of the cylindrical floater. Therefore, it can survive in the storm condition. If in another concept of floating offshore wind turbine, and if we have to reduce the motion of the system in this level, they will need much larger foundations. It will be much more expensive. So last movie of this slide is this one. Also in the storm condition, turbine is parking, not rotating. in this case, wavelength is large. In long wavelengths, the turbine system will move with the water surface. Heaving motion is almost the same as the wave surface, so it can be much safer. Some people may be interested in tsunami condition. Tsunami in offshore is similar to this condition. Tsunami is dangerous when it approaches to the shore, but this system will be installed in offshore. Therefore, distant from, if it is installed distant from shore, it will be safe even in tsunami. In contrast to this one, bottom fixed wind turbines are weak in tsunami because they are in shallow water condition near the shore, where the tsunami will be very strong. So, but we are still in the very beginning of this development. Actually, we need a scale up of this concept from the nearshore demonstration to offshore demonstrator and commercial plant. The first one, nearshore demonstrator will be 20 kilowatt in the regulation of Japanese environment. And after this small demonstration, we will go to offshore demonstration, megawatt scale pilot plant. I hope this will be supported by Japanese government or any government of other countries. After this demonstration, this concept will be proven. Then we will go to the auction of sea surface. Auction will be held by many countries. They will accept a bid of using the public sea surface for electricity generation. We will go into such a bid with larger companies. You may say this, our concept is stupid, but we are not alone. There are also similar concepts. This one is company name SeFeT2022. It is a Swedish company. The concept is similar to ours. They are also testing 30 kilowatt experimental turbine for several years. And also they are now building 1 megawatt demonstrator. This one will be installed December 2023 in offshore Norway. The size of 1 megawatt device will be this blade length will be about 40 meters. Still, it is small, but they are saying this can be a large wind turbine. In comparison to this SeFeT2022 concept, our concept is very compact. It is coming from the difference of the philosophy. In SeFeT2022 concept, they are not considering tilted position. Therefore, in comparison to the turbine size, they will use very large floater system. In our concept, the turbine is very lightweight design, and we will allow this tilted position. So the turbine, the floater foundation is much smaller than the SeFeT2022 float. Also, we are providing self-appending design. Self-appending is we don't require any crane ships or large cranes on the in the harbor. Therefore, infrastructure required for installing this turbine is very small. But sheet world does not show such a consideration of large device installation. Last one is we are considering a power takeoff system for high wave condition. In high wave condition, the turbine will receive a very strong wave load. There are simple mechanism. Wave load will on the generated power takeoff system. We have some ideas inside this part for avoiding the very heavy load. In our design, there are multiple generators inside this box, but generators are free from heavy wave load. So if there are some wind turbine engineers, they will say a vertical axis wind turbine is not efficient, but this one is very classic journal paper. It shows good performance of vertical axis wind turbine. This field test measurement was conducted by a Sandia National Laboratory, United States. The date of the journal is 90s, but the actual measurement was performed in 1980s. The wind turbine is 30-meter diameter curved blade type vertical axis wind turbine. It shows power coefficient, maximum power coefficient is around 0.4. Present modern horizontal axis wind turbines have a power coefficient of 0.45. So still it is less efficient than the present large horizontal axis wind turbine. But the point is, this one is this classic design, curved blade shape. Therefore, efficiency is only good around this part. This North Pole and South Pole part is less efficient condition. Therefore, if we will use straight bladed turbine, the power coefficient will be higher than this one. So we expect a power coefficient 0.45 to 0.50. So it indicates modern large vertical axis wind turbine can be more efficient than the horizontal axis wind turbine. But unfortunately, a recent large vertical axis turbine experiments are not public. But our simulation shows this is true. Large vertical axis turbine can be more efficient than horizontal axis turbine. Another point is in tilted condition, we can enhance the performance of the turbine. This is because in the tilted position, so this left side picture shows the tilted condition of the turbine. If wind comes in skewed direction, its frontal area will be larger than in the upright position. It will increase the performance. Actually, this experiment shows 20 to 30% increase of the power coefficient. So it indicates we don't have to keep the upright position of vertical axis wind turbine. So tilted position is better, but in onshore turbines, it is not possible. Or tilting the turbine is only possible in the floating wind turbine application. So we are intentionally tilt the turbine. This enhancement of the performance is also checked by the simulation. This one shows around tilt angle 20 degrees, the performance will be maximized. Another information is in the high Reynolds number condition, it indicates a large wind turbine device. Flow field is very smooth. This one shows the two-dimensional simulation. The color indicates the velocity in the horizontal axis direction. The blue color indicates low speed region. So you can see the wind is coming from the left. So the blue region behind the turbine indicates less energy or less momentum region. The energy and the momentums are absorbed by the turbine. In small turbines, the vortex shedding is much strong, and it will show less efficiency. But with the sufficient size, the vortex shedding is not so significant, and entire flow field is smooth. It indicates large turbine is efficient enough. Another simulation result is next one. This one is vortex shedding. So this shows the vortex. Blue and red color indicates the direction of the vortex. So this is another image of the large vertical axis wind turbine. No large vortex shedding. They are small, small shedding. They will not interrupt the efficiency of the turbine. We are also conducting three-dimensional simulation. The point is this complicated wake structure. So, for example, this one shows the sorry. This one shows the vortex wake system emitted from one of three blades. So as you can see, the wake of the vertical axis wind turbine is complicated and diffusive, not stable as the wake of the horizontal axis wind turbine. Flow is very complicated, but this complexity is good for the wind farm consideration. It is good because it will determine the required spacing of the turbines in offshore wind farm. The top left picture shows the stable wake of the horizontal axis wind turbine. It is this beautiful wake will long in long distance, and therefore we have to avoid the positioning of next turbine in this wake. Therefore, we have to have sufficient distance in offshore wind farm, the spacing of the horizontal axis wind turbine will be 5 diameter. So, but in vertical axis wind turbine, as you saw in the previous slide, the wake system is quite complicated. It is diffusive. And if the turbine is tilted, this wake has upward component. You can see this simulation results. Behind the tilted vertical axis wind turbine, there is upper motion of the wind. It indicates low speed part will go up and to fill the vacancy, higher wind flow will go down. So it indicates there will be a vertical mixing of the momentum. It indicates you can reduce the spacing of the turbine in vertical axis wind turbine wind farm. This effect is quite interesting. If we can reduce the turbine spacing by 10%, it indicates we can have 23% more turbines in the same sea area. So it indicates we can have 23% higher production and income of the wind farm. It is quite attractive consideration of the vertical axis wind turbine wind farm. So I will come back to the first slide of my concept. The valuation of the floating offshore wind turbine is only by cost of energy produced by this device. And now I'm showing 5 points. They lead to the cost reduction. First one is lightweight and low center of gravity turbine design. As I said, this will reduce the size of the float. And the rotating spar, rotating floating foundation will reduce the complexity of the turbine system. Seawater is the bearing support, so the mechanism is simple. It will reduce the cost of maintenance, cost of structure. And the third one is it allows tilted position. We don't have to keep this one in the upright position. If it can be tilted, we can further reduce the floating foundation size. Therefore, this float is much smaller than the conventional concept. Fourth one is low-cost assembly installation. Actually, present turbines are getting bigger and bigger. The present 15 megawatt turbine has a very high tower of 150 meters. Most of crane ships cannot reach this altitude. Therefore, if we want to increase the turbine size, we have to also develop crane ships or onshore large cranes. It is also expensive. But in this case, we don't require such lifting devices. The turbine will be assembled in this shape as a folded umbrella. It will be assembled on the flat ground, not inside the ship construction dock. And after assembly, it will go to the sheet surface, and by infusing sea water, it will append so it will be self-append system. And after that, the turbine will be open by the control of winch and wires. And after shape has been fixed, the turbine can be towed in long distance. So no heavy lifts indicates the charter fee of the we don't need a charter fee of heavy lift vessels, and required time for offshore construction will be also reduced. It will reduce the cost of project significantly. The last one is low cost turbine. This turbine consists of simple shaped members. It indicates we can use protrusion of the composite. Protrusion is we can provide the steel mold, but mold has only the section of this blade or shaft. The carbon fibers and plastics go into the sectional hole, and it will be pulled out to shape this thin and long members. The process is automatic, therefore it is very good for high labor cost countries like in Japan. These features will reduce the total cost, capital expenditure of the system by 50% or more. And also maintenance cost of this system is much lower than the conventional ones. And this system is very good for scaling up. Even if turbine system is, the mass of the turbine system is doubled, the support system is buoyancy. Therefore, the difficulty will not, the difficulty is almost the same, even if the turbine is much heavier. So we are considering this design will be a game changer of floating offshore wind turbine. So last slide this is a kind of conclusion of my talk. Future of floating offshore wind is not fixed nor horizontal. It means we consider it is vertical axis position and slightly tilted. And may the wind force be with you. Thank you for your kind attention.
Yeah, thank you, Hiro. So, is there any questions? Any questions from the audience? Are welcome. No? Any questions from the audience? Okay.
Hello. Yeah, Professor Akimo, I have one small question. Is it these floating axis wind turbines are limited to the any power limitation capacities, the power rating?
Actually, I think there is no limit.
No
Presently, horizontal axis wind turbine is the target of present horizontal axis turbines is 15 megawatt, and it is also possible for this floating axis wind turbine design. And if you need larger turbine, 30 megawatt, 20 megawatt, or 30 megawatt, reaching such a condition is much easier in this concept. Actually, scaling up the horizontal axis turbine is getting more and more difficult because it is mainly because the blade, the turbine blade is cantilevered, thin and long blade supported only at one end. It is quite difficult to increase the size. But in this vertical axis wind turbine design, the blade is continuous, both end supported style. Therefore, increasing the size is much easier in this concept.
Okay, thank you. And you mentioned that compact floating foundations. Can you throw a little more about this compact floating foundation? So,
it is the floating foundation is much smaller than the conventional one. In this case, this comparison shows horizontal axis turbine requires this size of float, but we need only this size. So required material, steel material is less than half, because cost of offshore structure is mostly determined by the mass of the steel used. It indicates this device is much lower cost. Also, this one shows the smaller wave load. Wave load is on this water surface penetrating area. So this the summation of this area is proportional to the wave load acting on this device. But in this case, in our case, such a surface for wave load is very small. It indicates mooring system is also less expensive in this concept.
okay. Yeah. Thank you for the clarifications. So if any more questions from the other audience, of course, it's welcome. Okay, so if no more questions, I take this time to give the concluding remarks on this session of the tutorial. So thank you very much, Professor Akimo, for your very informative and discussions on floating axis wind turbine applications. And of course, you have presented the details on this wind turbine fundamentals and the configurations and their design aspects, even with support of your 2D and 3D simulation studies. So, yeah. So it is very really, of course, the very informative and useful information. So thank you so much.
Okay, thank you very much for this opportunity.
Yeah, thank you so much for your contribution again. Yeah.
Dr. Ramin?
Yeah. Ravi, are you
Yes, sir.
there?
Yes, sir. Yes, sir. Sir, actually,
Yes,
yes.
hello.
Dr. Ramin, hi. Shall we
How are
start in
you?
next 5 minutes?
Sure.
Dr. Ramin?
Sure. Yes, I hear you.
Yeah,
You
yeah.
have my
Okay.
voice?
Thank you.
Yes.
Thank you.
Yeah,
Yeah, we
sure.
are going to start our next session in next 5 minutes. Is that fine with you?
Sure. Yeah, of course.
Okay. Okay.
No
Thank you.
problem.
Okay. Thank you.
Dr. Buba, if the timing is right, I can start.
Yes, one minute, Dr. Ramin.
Sure.
One
sure.
minute. Yeah.
Yeah. Mhm.
Boba sir, Narsan Rasa, shall we start, sir?
Yeah, Ravi. So
Yes, sir. Yes. Okay, sir. Yeah.
please proceed.
Yes, sir. Yes. Good afternoon, everyone. We'll be beginning our second industrial session. I would like to welcome our speaker, Dr. Ramin Amiri. He is a founder and CEO of Parastronic Corporation located in China, who will be delivering a session on electric powertrains for passengers and commercial cars, past, present, and future. It is a great honor for me to introduce our speaker, Dr. Ramin Amiri of today's second session, who is going to talk to us about electric powertrains for passenger and commercial cars, past, present, and future. He is very well known for his work in the field of electric vehicles. Dr. Ramin received his BSc degree from University of Tehran, Iran in 2008 and MSc from Michigan State University, USA in 2011. Both in electrical engineering. From 2011 to 2014, he was working as a design engineer on electric powertrains for passenger and commercial cars at Delphi, General Motors in California, and US Hybrid in California. From 2014 to 15, he was a PhD researcher at University of Wisconsin-Madison, working on deadbeat, direct arc, and flex control for Escava automation motor drives. Dr. Ramin found Parastronic in 2015, developing e-powertrains for passenger and commercial cars. Parkotronic has secured a major China grants for developing e-powertrains ranging from 30 kilowatt to 600 kilowatt for OEMs and tier 1 suppliers. Parastronic wide portfolios includes all types of electric motors, inverters, and gearboxes applicable to land, sea, and air e-mobility propulsion systems. Without wasting any time, I would like to hand over the session to Dr. Ramin Amiri. Over to you, Dr. Ramin Amiri.
Thank you very much for the opportunity given to me, and also the let me turn on my video, and also for the introduction. It's a pleasure to be able to present at the prestigious Sustainable and Future Electric Transportation Conference held at Hyderabad, India. And let me share my screen. Okay. The topic of this industrial session is electric powertrains for passenger commercial cars, the past, present, and future technologies. The vehicle's electrification is very crucial for our environment and also enables sustainability of transportation. Going from the past to the future, we have three different ways for land, sea, and air vehicles. The electrification wave for land vehicles is what we have seen so far in the industry. If I go back to the history, electric vehicle was made by General Motors in the 90s into 1995. After that, we have seen the Toyota Prius hybrid, and after that, we have seen many cars. And we have also seen electric buses and small electric trucks in the roads, maybe electric lift trucks in the factories. And the electrification trend is getting momentum. So by 2030, about 2/3 of the cars produced globally will be electric. The second wave will be for the commercial cars. That's the first one is for the passenger cars. The second one is for the commercial cars. And they are a little bit behind the curve for the passenger cars. So by 2035, we see like 2/3 of the commercial cars going electric, and the third wave relates to the C vehicles. Probably by 2040, the majority of the C vehicles will be electric, and the last one and the fourth wave will be related to the air vehicles. So around 2040 or 2050, basically we see the majority of the air vehicles going electric. Right. So for the commercial cars, basically we have two types, the on-road vehicles and the off-road vehicles. For the on-road vehicles, actually for both of them, we have 5 waves of the electrification. We have passed the first wave, which is the on-road because of the transit vehicles like transit buses. And the off-road ones are the light lifts like forklifts and lift trucks. The second wave relates to the delivery vehicles and also the medium terminal equipments. Some countries basically have passed this phase, or some countries haven't right now are in the middle of. The third relates to the medium freight or light site-specific trucks. The fourth wave relates to the heavy regional freight and container handling equipment and mining, the small mining trucks. And the fifth wave and the last wave relates to the long haul truck. And for the off-road ones, relates to the heavy site-specific agriculture, mining, and construction trucks. So this is what we will see in the future for commercial cars going electric, different phases that they will experience. So for electric commercial cars, we have 3 types: the battery electric vehicles, fuel cell electric vehicles, and also the hybrid electric vehicles. So in this picture, you will see the on-road class 1 to 8 commercial cars, and also the off-road construction, mining, and agriculture trucks. Basically, some of the OEMs have products, have cars, trucks in all these categories. Some have only focused on like Tesla has only focused on the battery electric vehicles, but some like Sunny, they have a wide portfolio. So they have fuel cell, hybrid, and battery electric vehicles at the same time. Okay. So the key challenges for electrification, they are mainly cost, range, charging, and maintenance. As for the cost, the 2 major factors are high purchasing cost, initial purchasing cost of the car, and also the high cost of ownership. For the range, the low driving range related to the battery. For the charging challenge, the shortage of charging infrastructure and the long charging time. They are the 2 obstacles we have for electrification as related to the charging. And regarding the maintenance of the car, the service life, and also the shortage of trained technicians. The last one, the maintenance, is not actually a big deal, but because it could be solved easily. But the previous 3 are very important. Some basically has been tackled, and so in the next few slides, I will talk about these three challenges and if the industry has overcome such challenges or is dealing with it at the moment. Okay, so the total cost of ownership of three cars are compared in this slide. For Tesla Model 3, Toyota Camry LE, and Audi A5. So when we look at the 5-year total cost of ownership of these cars, so I'll just read a few numbers so you get a feeling of why people nowadays prefer getting electric cars as compared to the gasoline cars. The purchasing price of the Tesla Model 3 is around $40,000. The Toyota Camry is $24,000, and the Audi A5 is $45,000. Of course, driving the car for 5 years, we have some some cost for the driver. The total cost of these two cars is shown, and the resale cost of the cars are also shown. So when we calculate the total cost of ownership for 5 years, Tesla will be around $35,000, Toyota Camry will be around $36,000, and the Audi A5 will be around $60,000. So you could see that basically buying the Tesla Model 3 is more economic than the other two cars. So it's not only that Tesla or electric cars are more environmentally friendly. That's of course one major factor that some buyers are looking into the EVs, but they also have some economic drive behind this move. For commercial cars, 6 factors actually form the total cost of ownership for a commercial truck, let's say, or commercial car. The first one, the initial cost to purchase or lease the truck. The second one is the routine truck maintenance. The third one is the years of vehicle repairs and parts replacement. The fourth one is the value of the truck when it's time to sell. The fifth one is the price of fuel or electricity. And the sixth one is the mileage per gallon or per kilowatt hour. So basically the final, I just read the final numbers. So the diesel truck total cost of ownership is around $1.51 per mile, whereas for an electric truck, this number is around 1.26 per mile. So it's more economic to have an electric truck nowadays than a diesel truck. So why we haven't seen the shift in the streets, in the markets so far, it's not related to the cost. So in the next couple of slides, I'll talk about the cost again, but for other components of the electric vehicle. And then I get to the basically driving range and also the charging problems that basically are the major challenges for the market penetration of these technologies into our nowadays lives. So the battery pack cost back in 2010, it was $1,100 per kilowatt hour. It was very expensive. So by 2020, it got down to the $157 per kilowatt hour. And by the end of the decade, 2030, it will be down to $63 per kilowatt hour. So, so as you see, the battery cost, it won't be any problem in the future. It's not much of a problem nowadays too. So the cost of the e-powertrain components is getting compared in 2020 and 2025. So the electric motor and inverter, the cost will be down around 20%. For DC-DC converters, we see a major cost reduction, like from $50 per kilowatt to $30 per kilowatt. And for the onboard charger, we see kind of like a minor, so from 50 to 35, basically cost reduction. So as you see, the costs are like decreasing 5 to 10% per year for the components of the electric powertrain. Okay, so for the range, if we look at the data for 2020, with a 500 kilogram battery pack, the range we could get from a battery pack was around 600 kilometers. It will rise up to 1,200 kilometers, so it will be double in 10 years, and that's pretty significant. So it solves many of the problems. Okay, so switching gears to the charging. So the charging time, nowadays it takes probably 30 minutes to like 40 minutes to charge, to fully charge an EV, a passenger EV, with a fast charger. By 2025, it will be reduced to 10 to 15 minutes. And also the charging power will be increased to 350 kilowatts by 2025. So here we could see also another problem getting solved. So the next one is about the charging infrastructure. So two important factors here are shown. One is the number of EVs, is the ratio. So if the ratio is the number of EVs to the number of charging points in different regions. So you could see like for China, we have about 5, that ratio is about 5, so it's pretty good. In UK it's around 12, US and Germany is around 20. So seems like some countries like have many charging stations. So that's probably not an issue in the future. It gets as it gets better. The share of fast charging, you can see on the horizontal axis for China is more than 40%. For like countries like Germany and US is around 15%. So I mean, that number probably will increase in the future, and it will basically support the EV industry. The technologies that could also help the EV trend. One of them is the fuel cell technology, which basically we will be glad to see that basically right now the fuel cell technology, I can say that the energy density is not the problem. The problem is that when you look at the fuel cell from A to Z, I mean how the hydrogen is produced and how it's getting into the fuel cell stacks in the car. When you take into account the whole process, unfortunately, it's not as efficient as it could be. So in that case, the battery is a better technology than the fuel cell. That's what we have. We see in the market and the industry right now. But in the future, this could, of course, could change. The second technology that could really help the EV transition is the battery swapping. And of course, the battery swapping is could be done very fast. So this could solve the charging time problem to a significant matter. So and some of the companies are working on this. technology. Right, so switching gears to the electric powertrains. So for passenger cars, we have various configurations. We have cars which you could see a single motor on the front axle or on the rear axle. You could see cars with the dual motors supporting both axles, triple motors, and also four motors, quad motors applications. So we are giving some examples and some spec of the vehicles, so you get a feeling about the electric powertrains used in various cars that you see on the streets nowadays. The power, like for like the front wheel e-powertrain and single motor ranges from 30 to around 150 or 200 kilowatts. Cars such as Nissan Leaf, Mercedes EQV, and Chevy Volt are examples of this. On the rear axle, we have powertrains ranging from 30 to 250 kilowatt, like the old Tesla Model 3, Mercedes EQS, BMW i3 are examples of this e-powertrain architecture. For dual motors, the power, when I talk about the power, right now we have several motors here. So I mean the sum of the power of all electric motors that we have in the car. So in this case, we have two motors. So the sum of the two motors power is from 200 to around 600 kilowatts. Cars such as Tesla Model 3, the new one, the Neo ES6, Nissan Ariya, Porsche Taycan are examples of this architecture. And for the triple motors, the power ranges from the total power ranges from 400 to 800 kilowatt. You could see on the vehicles such as the Audi e-tron, Tesla Roadster, Tesla Model S. And for quad motors, actually, you could see it on the super sport cars such as the Neo, Rimac, Lotus, and produces a lot of power from 400 to almost 1500 kilowatts. So these numbers and these configurations help you better understand the various architecture we have for electric powertrains. And okay, so the next one is for the commercial cars. So we have single motor architecture, dual motor architecture, triple motor architecture, and quad motor architecture on one axle, two axles, or on wheels. So, okay, examples of this. The single motor for the front axle. You could find it on the cars such as Mercedes-Benz, the ES Sprinter. So, and the range of the power is from almost 80 to 200 kilowatt. On the rear axle, the single motor, from 80 to 200 kilowatts. You could find it on Volvo buses or trucks and Ford e-Transit vans. So for two motors, you could find it on cars such as trucks such as Mercedes-Benz Gen H2 truck. The power is 660 kilowatt. And we have another configuration for two motors. The power ranges from 200 to 400 kilowatts, which can be found on the Mercedes Actros truck, Volvo FE, and Volvo FMX. Okay, so the dual motors also you could find it on the Ford pickup truck F-150. The power is around 285. For the triple motors, there's an interesting architecture on the Volvo FM truck. Three motors supplying one axle. The power is around 500 kilowatts. So for quad motors, the Lordstown endurance pickup truck or the Rivian pickup truck, which have got a lot of attention the last couple of years. The power is ranges from 440 to 620 kilowatt. And for Tesla semi-truck, which is not yet in the market, but it has 4 motors supporting each wheels. The power is around 800 kilowatts. Okay, so now you're familiar with the different powertrain configurations for passenger and commercial cars. Here, we talked about the integration of the electric powertrain components. So for electric powertrain, we have 4 major components. We have the electric motor, we have the inverter or MCU, we have the gearbox, and we have the differential. Like sometimes you can find some products from suppliers combining 2 of them together, like the motor and inverter. That's type of integration, we call it 2-in-1. Like Bosch, EM Power, Estate, they have products with this type of integration. The 2-in-1 integration combines motor, inverter, and gearbox. Sometimes you could find 2 motors and 2 inverters and 2 gearboxes in a 2-in-1 basically integration package. Like from Daimler, Mercedes, 4-in-1. We need to also include all the components. So we need to add the differential as well. And companies like BorgWarner, AVL, Haffer Powertrain, they have a product with this type of integration, which could save cost and also, so in the next slides, I will talk about the vehicle chassis because powertrains or chassis are closely related to each other. And when we are electrifying a passenger car or electric basically, we need to take into account the chassis limitation, so we cannot use any type of the basically integration configuration as we wish. We have to take into account many limitations, including the chassis limitation. Okay, so design of the chassis is very important to the OEM because each OEM for the manufacturing of the passenger cars or commercial cars, basically they need to have various types of chassis. Nowadays, a flexible and modular chassis is preferred, so they can easily fit in different components for different type of cars that they manufacture. And so here we could see chassis from Mitsubishi, BYD, that they have produced for the passenger cars. I've shown more of these chassis platforms from Geely, from Hyundai, Volkswagen. Okay. So for commercial cars, we also have like different OEMs and suppliers producing different chassis platforms to enable the future electrification, mainly basically for class 1 and 2. You could see chassis manufactured by Canon, Rivian, and Ford. For class 3 and 5, you could see Hino and Lee, making very flexible and wonderful chassis. Bluebird chassis for class 5 and 6 electric buses could be used. So various chassis for various cars and platforms. Okay, so right now the technology for inverters using electric powertrains, we have 400 volt and 800 volt technologies, and also the switches used in inverters could be silicon IGBT or silicon carbide MOSFETs. Of course, the silicon carbide MOSFETs have the advantage of higher switching frequency, so the total power density will be much higher, and so we will end up having a compact system. So that's the preferred way of doing that, especially for passenger cars. Okay, so here we are showing some of the products from various suppliers, and also against the maximum power. Showing that the power going from around 30 kilowatt to 500 kilowatt. That's what we have in the market right now. So from Borg Warner, Cascadia Motion, State, and different suppliers, we will have different MCUs for different e-powertrain applications. Okay, so another major component for an electric powertrain is the electric motor. So for different passenger and commercial cars, different motor configurations, motor topologies is used. Probably the most popular one is the permanent magnet synchronous motor, the interior permanent magnet, or IPM we call it. Another topology is permanent magnet synchronous reluctance, which is not much used, but you could find it on like cars like Tesla Model 3. The actual PMSM, basically very few companies in the world are developing this, but it's quite useful in some applications, especially commercial for commercial cars. Companies like Banggood are working on this technology. The old design, old technology, I should say, the induction machine, induction motor, in use in some applications, but it's not a superior technology compared to the other topologies I introduced. The switch reluctance motor on some off-road commercial cars, you can find this type of motor, like on the Caterpillar off-road vehicles. And the BLDC is also technology, a motor topology that could be used, but is not used very much for passenger cars. For commercial cars, we have seen that. Here we are not discussing about the electric motors, but you could see on the electric motors, the hub motors is they have the major technology uses the BLDC. Okay. So the power basically for electric motors ranging from like 20 kilowatts to 1000 kilowatts is provided by various suppliers such as Pangut, JJE, Vyasa. Vyasa is also producing the axial flux motors, which was acquired by Daimler probably a year ago, Danfoss, Bosch. So many options we have for the electric motor in the market. Okay, so I want to switch gear and talk a little bit about the automotive software, the trend, the history, and also the future. Because as you have heard of the phrase, which is very common nowadays, the software-defined vehicles. So software is becoming more important in the cars, and here we will discuss it a little bit. So here is just a comparison of the cars, which like the number of codes used in cars as against the aviation industry. Like for example, the F-35 jet, the total line of code used is 25 million. As for a 2020 car, the number of codes is more than 150 million. So the car is getting more complicated when it comes to the software. So and actually there are a lot I can say about this, but to make it brief, by 2030 we are looking at over 1 billion lines of codes, and so we need a lot of talents, expertise in this area, and it's not only related to the powertrain of the car. I'm talking about the whole car. So it's a very interesting area to work at and look at and follow the trend. So we divide the software of the whole car into 6 different domains. One is the chassis. So I just named the 6 domains: chassis, powertrain, infotainment, autonomous driving, safety, and body. And also this whole system kind of will be organized and managed by an operating system and some middlewares in the future. So the software trend, so we had the Gen 2 architecture. This was called an integration architecture before, and in 2010, by 2020, we got to the Gen 3, which is a domain centralized. So each domain, the 6 domains I introduced in the previous slide, each one of them has a domain control unit and so forth. By 2025, some of these domains, such as like, for example, the powertrain and the chassis domain, they will be integrated together. And by the 2030, the vehicle centralized domain will be introduced. So, so you could see many electronics integration in the car, and the car will become something very similar to a server. So to handle the computation of basically all the softwares that we have in a car, we need very high computation processors, and that's where we get to by 2030, the vehicle centralized architecture. I don't want to get into the details of this, just just provide a big picture of the car software. You can see the e-powertrain chassis, body safety, and autonomous driving and infotainment domains. So each one of these domains basically includes some ECUs, electronic control units, that they are communicating with the domain controller, and all these domain controllers are connected to a central gateway controller. So that's a central unit which manages the whole software of the car. So for the fourth generation, which is called the domain centralized, basically domain centralized generation, you could see the various domains integrated together, such as the powertrain and chassis, autonomous driving and safety. So they get integrated together, and basically this integration, of course, reduces the cost of the hardware and also eases the communication between different controllers in the car. The fifth generation is where we get the basically the ultimate integration for electronics of the car. So we have the powertrain chassis integrated together. We have a body which also acts as a central vehicle computer, and basically the autonomous driving, safety, and infotainment. They will be running on an open server platform, or you could also call it a high performance computer, a high performance server. So this is what we will see in the future. As for the software of the e-powertrain, I think on the entire car, I could not really separate these two because they are kind of they have should look at it as a single unit. And here I skipped some of these slides. Actually, for Gen 2 and Gen 4, here you could see the software used basically for the software architecture for Gen 5. It looks very similar to a server. I mean, the IT guys know this very well, and you could see the softwares for different applications on a car could be looked at as a kind of like a virtual machine or an application running on an operating system. So this is the future, and the exciting part about this is that we will probably have a sixth generation that we don't do the computation on the car. We just rely on the cloud computing. So we send all the data to the cloud servers. They do the computation. So by that time, we'll probably have right now we have a 5G communication protocol. At that time, we will probably have a 7G or 8G. So the latency is pretty low. So that's acceptable for basically all the targets we have for a car. It could be autonomous driving. It could be different applications, any application within a car. So that's really the sixth generation of the software and hardware, electronic hardware that we will have in the future. I hope my presentation was useful, and I'm open to the comments and question and answers.
Yeah, so is there any questions? So you're welcome to ask the question to the speaker. So any questions? Okay, so if no questions, yeah, so I take this moment to give a concluding remarks on this session on this electric power trains for passenger and commercial cars. So thank you very much. So Dr. Ramin Amiri,
Pleasure.
for your enlightened discussion on this electric power trains for passenger and commercial cars. And of course, this discussion provides this vehicle electrification, their essence of on-road and off-road vehicles, and also the discussion on the challenges in passenger and commercial vehicles, uh, and also the details on this charging time issues, fuel cell technologies, and the different architectures of passenger and commercial vehicles. And also we have discussed the chassis platforms for various models. Yeah, so it is a really, and also the electric motors, the types of electric motors, which are the propulsion systems for the EVs. And finally, also the discussion on the software, automotive softwares. Yeah, this information is really useful for the audience and for the community, research community. Thank you so much for your
Pleasure.
enlightened discussion. Thank you so much once again, Dr. Ramin.
Thank you for the opportunity given to me, and also hosting this wonderful conference. I hope all the audiences enjoy the sessions, industrial sessions, paper sessions, and so again, thank you for the opportunity, and I hope everybody enjoys the conference.
Thank you. Yeah. Yeah. So thank you all. So this is the end of the session 2, and I think we have a break of 1 hour, I guess. Am I right, Ravi? So
Yes, sir.
Dr.
Yes, sir.
Ravi?
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Our next session
So-
is going to start at 5:30, sir. Yes, sir.
Yeah. Okay. Fine. So thank you. So then let us come back for the next session.
Okay, sir. Thank you, sir.
Thank you very much.
You are-
Yeah, thank you. Thank you, Dr. Ramin. Thank you very much for our contribution in our conference. Thank you very much. Great
Sure,
day.
thank
Yeah, thank you. Good day.
Okay.
Okay, thank you. Good
Have a
day.
good day. Bye-bye.
Okay, bye-bye. Hello, Rana.
Hello. Yeah, I'm audible.
Yes, yes, yes. So we'll start in the next 2 minutes.
Yeah, no issue.
Fine, right? Okay, thank you. Fanindra sir, shall we start, sir?
Yes, sir. You can start, sir. I think people will join. You
Yes,
can
sir.
start.
Yes, sir.
Otherwise,
Yes,
it will
sir.
take time.
Yes, sir. Yes, sir. Yes. Okay, sir. Thank you, sir.
You
Yeah,
can
good
share
evening.
the screen, sir, profile.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Sharing, sir. Yes. Sir, my screen is visible, na, sir?
1 second, sir.
Yes, sir.
Yeah, visible, sir. Visible, yes.
Okay, sir. Thank you, sir. Yes, sir. Yeah. Good evening, everyone. For the second international conference on sustainable energy and future electric transportation, we will be beginning our third industrial session. I would like to welcome Mr. Ashwini Kumar Rana, co-founder of Vanix Technologies, located at IIT Ropar, who will be delivering a session on the role of FPGA technology, its opportunities and future. It's a great honor for me to introduce our speaker, Mr. Ashwini Kumar Rana, for today's third session. He is very well known for his work in the field of power and energy domains. Ashwini Kumar Rana has received his BE degree in electrical engineering from Mumbai University in 2012. He completed his PhD degree in electrical engineering with IIT Ropar, India. His research interest includes drives and control for electric vehicles, control of switched reluctance motor drives, inverter design, sensorless control, and robust control. He has more than 15 papers in high-impact IEEE transactions and international conferences. He has a vast experience in industrial and academia in the variable drives and converter areas. He is also co-founder and CEO of Vanix and Lozier Private Limited. Vanix technology is solving the logistics sector problems with high-tech solutions. Vanix Technologies is working on advanced FPGA controls using AI algorithms. Without wasting any time now, I would like to hand over session to Mr. Ashwini Kumar Rana. Over to you, Mr. Ashwini Kumar Rana. Rana?
Yeah, thank you so much. Am I audible? Hello.
Correct.
Yes, sir. You are audible, sir. Yeah.
Okay. Let me present. Let me present my screen.
Please.
So my screen is visible.
Yes.
No, not.
No, visible, sir.
Okay, sir. Okay, sir. It is not visible. Okay, sir. Yes, sir.
So thank you very much for having me on this IEEE conference. Basically today it's not about the talk. It's a kind of discussions, not a more of a talk, but we'll talk about the role of FPGA technologies and its opportunities and the futures. How FPGA are changing, actually changing the role in the technology, as well as how actually FPGA making a very good contribution in all the domains in the technologies. So basically today's content is basically we look first understanding that what exactly the FPGA architectures, how exactly the FPGA architecture is made, how exactly it is different from DSP processors, or you can say that a kind of microcontrollers, or you can say that ARM kind of processors. And then we'll go for in detail with the FPGA portfolios. Basically, this is again that how exactly FPGA technology is developing in market. If you'll see that what kind of FPGA chipset were there, and when you selecting any FPGA for a particular applications, what are the things you should watch, or what are the things you should see in the FPGAs. So this kind of FPGA portfolios we'll see. And when we look into the FPGAs, so today FPGAs are using from low-end applications to high-end applications also. So how exactly the big players like Xilinx or Intel or other groups are working in this kind of technologies, and how exactly they will impact in the future's technologies. Then surely we'll see the selection of FPGAs, because the chipset were theirs. Basically, if you look into the Xilinx chipset were there in that, let's say Spartan or RTX or a kind of Kintex chipset. But in that chipset also, how you have to select a particular FPGA IC for your applications, and when you go for any data sheet or kind of things, what are the things you must see while selecting the FPGA. This is very, very important, because each FPGA IC actually vary with the resource optimizations, as well as FPGA IC is very important in terms of cost and all. So for example, your application is, let's say, low end applications, and if you wanted to select this if you selected a high end FPGA IC, so that kind of problems which is not economical or viable for the industry. So this is very important, that how you select the FPGA. So first we must know that exactly the product which I'm making, or the R&D where I'm making the prototype or kind of things, what exactly the maximum utilization, what kind of power, what kind of resources I need from any FPGA IC, and based on that then we go for FPGA selections. So this we'll talk in some details. And then we'll talk about FPGA applications, that how FPGA applications were there, in how many domains now FPGA are using, and even in futures, what are the things where actually FPGA are making a prominent roles. So basically now in the previous 7, 10 or 8 or 12 years back, there is a lot of applications where FPGA won't play a prominent roles. But today in the world 2020 or 21 or 2022, you will see that there is a many FPGAs which actually making a place in a very different kind of applications, which we didn't think 10 years back. So obviously that kind of application we will discuss, and then we will discuss that the FPGA role basically in power electronics also, because how exactly power electronics shaping and using the FPGA's energy to making the application more viable. So in this basically we look one kind of application, let's say we'll look into the EV application or DC to DC kind of converter applications in details, and then we'll look that okay, how exactly the FPGA playing role there. And then obviously the customization of FPGA, where VANIX basically working, and how exactly the customization is important, and how we should know that it can play a bigger role in the industry as well as the academia. And then the last we'll talk about the VANIX board, means how our company is working, which kind of boards, what kind of project we are dealing and all. It's a very small introduction about the VANIX. VANIX is basically, we are a very young startup. Basically, Logier is a bit old startup 3 years back, but the VANIX is a very young startup. It is founded in 2021, and the founder members are all doctorate students basically. So now most of the peoples are doctorate in this. In the VANIX technologies, basically we are working on the advanced FPGA controllers for every kind of application. So we covering the defense to energy, electrical vehicles, mechatronics, communication, any kind of applications, how we can replicate into this, and this kind of application, how it can be beneficial for industry as well as academia. So with the vision that how we can help the R&D peoples of the academia as well as the industries. Okay, so with that aim, we actually founded this company, and we having already completed some kind of projects also executed, and some kind of products already in the market we have. Okay, so let's start with the FPGA. So FPGA is just silicon chip that everybody know that, but it is a reprogrammable silicon chip. So if you starting with the history, so we know that previously it was logic controller, CPLD kind of thing. After that ASIC devices comes, but that devices are completely design specifics. Okay, so if there is a very high capital gain cost, we have to be paid. So for example, for a particular applications, we have to be make a controller, ASIC based controller. So basically the design process take a lot of time, and that once it's designed, it is fixed for that applications. Okay, so for low kind of things or R&D kind of things, ASIC devices basically a very costly devices. So then we come up with the solutions like FPGA kind of solution. So FPGA is a kind of a programmable silicon. Hello, yes.
Sir.
Yeah.
Hello, sir.
Yeah.
Director, sir. Sir.
I'm able.
Sir. Sir, Adi. Oh, sir.
Should I continue? Hello.
Yeah, Rana, please continue. There was
Yes,
some
sir.
disturbance. You can continue, please.
Yeah, actually some voice is coming, so I thought somebody
Yes,
asking
yes, yes,
questions.
sir. Because without mute, he is speaking in the phone. You can continue, please.
Yeah, okay, no issue. Okay, so then we were on FPGA. So FPGA kind of a silicon chip where we can program, program again and again. So what is the basic difference between an FPGA technology and the processor or ARM processor kind of technologies? It's very simple. When we look into the ARM kind of processor, ARM Cortex processor or microprocessor, so that is also a kind of embedded solutions, but where what we do, we actually doing a software kind of instruction set, and then we simply putting that software kind of instruction on the particular ARM Cortex processors or any microcontroller kind of things, where the instruction set, through instruction set only we can manage the things in a way. So where exactly we cannot change the hardware in a very good way. In the FPGA, what exactly happened? Basically, we are changing at the hardware level, basically. So it's a kind of open paper sheet where exactly through the digital logics, through and or any flip-flop kind of things, you make circuits, and with that circuits actually you can realize any applications. Okay, so when we're talking about the processors, we basically main focus on the software kind of things, where we don't have the liberty to change the the hardware design kind of things. But FPGA, where exactly we change the designs through the RTL synthesis, we can we can write the code, and after writing the code we can change actually the complete logic. But other microprocessor or the DSP processor don't give you that liberty. So when I'm talking about FPGA, it's a kind of hardware programming, you can say that, and when I'm talking about microprocessor, this is a kind of software programming. So again, it is create a personalized hardware. So again, if somebody asks you, then again in FPGA you can itself, for example, I'm taking one example, there is a ARM Cortex processor or any DSP processor, so you can create same DSP processor on FPGA also through the logics, the digital logics kind of things, because it's just a white paper, you have to be create the logic and you can do these things. So FPGA technology come up with that features basically. The second thing is this, that FPGA basically having a parallel nature. Basically the thing is this, that when we are working on the FPGA, parallelism is very important. So in the next slides we will talk about what is the parallel communication, parallel execution and the serial execution. But the parallel nature is that the multitasking can be possible in a very easy way. There is a lot of things where exactly you assign a multiple loops and multiple tasks in one FPGA and they can run parallel. So for example, if I'll give you example, let's say you have to generate a 48 PWM for, let's say, for any applications. Okay, so that 48 PWM with different frequency, with the different sampling rate, it can be parallel executed on the FPGA very easily, where the microprocessor or the DSP kind of things find very difficult to handle it, because there it is a serial wise execution, and that will anyhow slow down the process. So when it comes to the FPGA, it's a hardware base, so that's why the reliability and the processing speed is very high. Now, if you look into the FPGA architecture, this is the basic FPGA architecture. Here I wrote that Xilinx FPGA structure, but any FPGA structure, if you look into the Intel kind of things also, there also the structure is somehow same only. So if you can see that the outer part here, blue one, this is the IO blocks, and this yellow part we called as configurable logic blocks. Okay, where exactly we are making the configuration, and this white lines, that is called programmable interconnects. Okay, so these white line actually connecting lot of configuration logic blocks together, and then through this we can realize any kind of logics. Okay, so again, if you look into this configuration logic blocks having slices. So if you go into any FPGA IC, for example, let's say if you wanted to select the Xilinx FPGA IC, okay, so there you will see that in the data sheets. Okay, this IC having this number of LUTs, this number of logic cells, this number of slices. Okay, so again, each is configurable logic blocks contain slices as well as logic cells. Okay, now what exactly slice? Each slice contain many logic cells. It can be 1, 2, 4, 8 logic cells. Okay, and each logic cell having its own LUTs. So what is LUTs? Basically LUTs is a kind of logic, it's a lookup table kind of things. Now look, it's very common to understand that how it is a digital circuit realization. So basically what FPGA do, FPGA can realize any circuit through the logic circuit. So let's say AND gate is there, OR gate is there, or NOT gate is there. Okay, so for every gate what we do, we are not doing actually we are not realizing these gates differently. What we do, we make simple kind of LUTs, different kind of LUTs, and through these LUTs we having a different kind of gates. Let's say we having one LUTs in which we can realize AND gate, OR gate together kind of things. Okay, so these LUTs were actually in the configuration logic blocks. In this CLB also, basically there is a set and reset kind of things, there is a flip-flop inside this, and there is a clock also this side things. Okay, again this configuration logic blocks having RAM and also set and reset. So what exactly lookup table, actually each implementing logic function truth table. So truth table, it can be of AND or any kind of logic truth table, it can be implemented through these LUTs. Okay, basically again it can implement fast arithmetic operations like increment, decrement, addition or subtraction kind of things. Okay, then memory element also is be there in this only, and in this memory elements we having configuration flip-flops and latches. So based on the flip-flop also we can realize the different logics. We having programmable clocks also, so in that obviously how much clocks you need, what kind of clocks you need, this kind of things we have. Okay, so this is the basic architecture of this. And again if you look into the detail of that FPGA IC, what exactly the FPGA IC, so basically it having a lot of LUTs, and these LUTs basically in the configuration logic blocks. Okay, and these LUTs basically connected through different kind of these horizontal lines which we call that switch box. Okay, so based on our logic, these switches are connected to each LUTs. For example, I need to make some mathematical operations based on different logic cells. Okay, so might be I have to use lot of LUTs, lookup tables. Okay, so these lookup tables are connected through each other through these wires, kind of wires, and which we call at the switch box. So this is actually the architectures. Those who are working on applied kind of things, those who are not working on VLSI domain, like those people who are working on electrical vehicle domain or communication vehicle domain, or you can say that drones kind of things or any kind of things. So this kind of things they doesn't required, but obviously how actually FPGA works, that is important. Now FPGA architecture, previously also we discussed that FPGA actually giving you a complete parallel application. So I'll give you a very simple application in conventional DSP device. For example, if you have to implement something like first order filter kind of things. Okay, so if you wanted to do one FIR filter kind of things implemented on DSP space, let's say 256 tap you wanted to do, so it will take 256 clock cycles. While in FPGA programming, in parallelism, you can execute these things in one single clock. Again, I'll tell you, for example, if you wanted to do the PWM pulses, let's say for 48 PWM pulses. So 48 PWM pulses, it will go in sequence phase. Okay, so the last PWM pulse which you realize, it will having very low sampling rate. Okay, so for example, if the crystal of any crystal in any DSP or kind of things having let's say 100 megahertz crystal, but after coming sequential things, it will decrease the clocks, and after that whatever as a IO you will get it at a very low sampling rate. But in FPGA, what kind of things, any things you can execute parallel. Okay, so for example, any PWMs you can execute that same PWM in megahertz also. So this kind of things actually parallelism give you this kind of unique features. One more example I'll tell you in the DSP kind of things and all. For example, you wanted to execute one program. That program is, let's say, one instruction. Let's say the instruction is a plus b ka whole square. Let's say a plus b whole square. So if I actually do this must be a square plus b square plus 2ab kind of things. So in DSP and all other processor, what exactly happened? A into a will take one cycle, then b into b take another cycle, then 2 into A into B, take another 2-3 cycle, and after that you will add this again, take 1 cycle. So what exactly happened to perform a single operation like A plus B whole square, it will take 8 to 9 clock cycles. Okay, but in FPGA what exactly happen, A to A, B to B, to A B, and adding all these things, they can be done all in parallel single clock. Okay, so you just imagine that how fast speed processing happening when it comes to a complex kind of algorithms that we have to be managed in the FPGA. Okay, so FPGA give you this kind of parallel execution. So this is one of the advantages that FPGA have. Okay, now what are the kind of FPGA portfolios we have? Now, if we look into the different kind of FPGA in the market, we have Intel FPGAs also. Previously it was Ultra. But now it was actually taken by Intel only, and then Xilinx FPGA was there also, lattice PC also there, CPLD kind of this. But the major market share in the market, if you'll see that the Xilinx AMD, that is AMD owned company now, and the Ultra, that is Intel owned company. So now Intel and Xilinx, or you can say that AMD FPGA is only taking the whole market share. No, and both the companies are making low cost FPGAs to the high-end FPGAs. So now what exactly the FPGA portfolios, how exactly when you go for any FPGA selections or you wanted to do those things. Now in Xilinx, basically 4 kind of chipset were there. The one is Spartan, which you can see on the first, then there is a RTX chipset, then there is a Kintex chipset, and then there is a Zinc chipset also. Now in Spartan also, most of the ICs are obsolete. So now in the market today, you'll see that you'll get Spartan 7 ICs only. Spartan 6 were also, just offing from the market only. So Spartan 7 now it is available, and it is a 28 nm chipset. Okay, so what exactly the best way in this? For example, if you wanted any kind of application which is required only IO kind of things, you don't require a very hard calculations. Okay, there is a lot of sensors were there. Let's say sensors were there, a lot of sensor, you wanted to integrate all the sensor on single board. Okay, so for that kind of things, Spartans is very good IC. It is IO optimized, means you will get lot of IOs. And when I'm saying there is a lot of IOs, basically what it means you have a lot of sensors, and the lot of sensors you can integrate on the these ICs basically. Okay, when we look into the RTX chipset, obviously RTX chipset also having optimized IOs also, but these chipset basically made for high communication, basically transceiver optimized it is, so you can transfer the data in the giga samples per second also. Okay, so this chipset basically made for that also, but it doesn't mean that it is not good for other applications. It is also taking the application of like sensor integration, image processing, power electronics kind of things, where you need a precision and control kind of these things. So there also RTX chipset playing a bigger role. So it's not only the, but the why I'm saying a transceiver optimized, the reason is that it is best suited for that. Okay, but it contain all the features of Spartans also, because it is a higher version of Spartan, you can say that. So it contain all the things also. But for example, you doesn't require that kind of application, so you simply use the Spartan IC also. Then if we go for the Kintex and the Zinc optimized, so these are SoC. Basically Spartan and RTX chipset, if you leave ultra scale, these are pure FPGAs basically. But if you look into the Kintex and the Zinc, these are called system on chip kind of things. System on chip means with FPGA they having ARM processors also inbuilt in the chip itself also, because everything we cannot realize on the FPGA also. Basically what happened today, we saw many computer vision applications, many AI kind of applications where we need a ARM kind of processors capabilities. Okay, so everything designing on FPGA is sometimes very difficult. So what exactly this Zinc chipset is a system on chip. Okay, so in this mainly basically you have a ARM Cortex processor also that actually used for the video kind of thing, image processing kind of things. I'm not saying that this video and image processing cannot be handled by FPGA. It can be handled by RTX chipset also. If you look into the RTX highest chipset, that also handling image and video processing. But today in the world we need very high very low latency rate, and what exactly we need very high video processing, like a 4K video processing, or we need to be connected with the cloud or AI kind of thing. So there, what actually these companies doing, they actually combining the power of FPGA as well as combining the power of processor, and then they come up with the solution that, okay, this is the chipset, let's say the Zinc chipset or Kintex chipset, and these chipset actually basically fulfilling the lot of applications which are basically, you know, image processing, video processing kind of things, or sensor fusion, or kind of any application they can cater very easily. If you look into the Zinc, for example, Xilinx Zinc, it can easily take the 4K video, and it can easily, you know, give the 4K video also. So encryption, decryption of kind of these things are very easy in the Zinc, because here actually along with the FPGA, they are integrated with the ARM Cortex A73 kind of processors also. So that capability they are handling. So how now companies are now working, their chipset are pure FPGA chipset also. If you look into the Spartan or RTX kind of chipset, along with that they having the chipset like Kintex and you know, Xilinx chipset also, they having a lot of things together on the single chip only. One more category is there, which called as system on module basically. So now if you look into this now, basically again Xilinx and Intel both come up with the solution that everything we cannot put into on the chip only. So basically now they are selecting the best FPGAs where parallel operations can be handled very good, and after that on single modules they are doing like memory kind of things or ARM processor on single modules. So this kind of solutions also there, and they are you know, working in this solution only. Previously 7 to 8 or 9 years back, if you look into this, basically the AI kind of thing or computer vision kind of things, FPGA was not the first choice. The first choice was NVIDIA kind of processors. Today also, if you look into this GPU processing things, or you can say that training any big data, we still using NVIDIA's only. But now company are fighting towards this, and they are you know, trying to be take system on module kind of things, so that some things we can realize on the FPGAs also. So in futures, many things you will see that where we are using NVIDIA kind of GPU. So many things you'll see that many people are working now on FPGAs, and they try to realize the, you know, GPU kind of capability on FPGA also. So this research is also going on, and hoping in the next decade we'll see that this kind of research is going on. Now obviously this is the, you know, this is a kind of chipset basically, that okay, this is RTX chipset or this is a Spartan chipset. But if you go in detail also, so let's say this is the one you can say that, so this is RTX chipset. So this in RTX chipset also you have a lot of devices. Okay, so you have you know, 12T to 200T. So 200T is the highest chipset that is available now on RTX. Okay, so how will you going to select? Obviously you decided first that okay, I'm going to select the RTX chipset, but in RTX also there is a lot of families of you know, FPGA. So how exactly you going to select the exact FPGA? So it's again depend on the logic cells. We already we discussed that how many slices would be there, how many logic cells would be there. Okay, so you can see that as the chipset is going to increase at the 200T, we having 215K logic cells. So when I'm saying 250 to 15K logic cell, means it can handle a lot of computational burden. So again, it depend on your choice that how much algorithms you going to handle. So you have to first see that how much logic cells you can provide. So for example, I'll tell you, for example, a small DC to DC converter application you have to run. Okay, so for small DC to DC converter application, so let's say small DC to DC converter, so maybe you don't have a very high computational burden, so you can go to the basic 12T device, okay, where you need only IOs much. Okay, so again you can do these things. Again, there is a one more thing that is called a DSP slices. Okay, so here also 40, 45. So what exactly DSP slices? These DSP slices having a dedicated multiplication and additions. So you know these things that when we implementing any algorithm, these are just a maths. Okay, multiplication, addition, and all these things. Basically, whatever the DSP processor which we are using, you know, previously or different, that also basically doing a image processing kind of thing. And when you look into the detail in image processing, it's just a matter matrix multiplication or, you know, addition, subtraction, this kind of things only. So DSP slices tell you that how much DSP slices. So for example, this 40 DSP slices there. So one DSP slice can handle 2 multiplication, 3 multiplication, and depend on the again ARTIC chipset. Okay. So again, if your algorithm is very heavy there, the multiplication kind of thing, the addition kind of things required are huge things. So based on these DSP slices, you can select your chipset. Okay. After that, the main thing is that the maximum user IOs. So there again, IOs play a very important role. For example, let's say if you selected 200T, so you having 500 IOs. When I'm saying 500 IOs means you can use these IO to integrate lot of things on a single board. Okay. And when I can integrate lot of things on a single board means I can ultimately reduce the size of the board a very good way. I can optimize whole system. I can reduce the cost also. And the second thing, that I can increase the efficiency of the whole system, because if you make all the peripheral, there's a lot of peripherals available, and you bring all the peripherals. Let's say you realizing multi-level inverter kind of things, where you require, let's say, voltage sensor, current sensor, let's say 16/7 current sensor, 16 or 17 current sensor, voltage sensor kind of things, and multi-level inverter I'm talking. So there you require a lot of ADC channels, DAC channels, so where you require a lot of IO. So you have to go for higher chipset. Okay. And when you go for the higher chipset, basically what happens, you can integrate maximum ADC, DAC kind of things on a single board or single device. So that kind of things you can do. So these are the things we have to be keeping in mind when we selecting our applications. Basically, again, when we go for FPGA selections, again we have to see one more thing. So here again we having ARTIX chipsets, and along with that we having the different packagings also. Okay. So I'll tell you one more thing, is it's very important. Now I'll tell you, there is a, let's say in this slide you having 100T also in the last, and 200T device also. Okay. Now in 100 and 200T, if you see, logic cells are double basically, correct? And even you see a DSP slices, that is also double, 240 to 740. And if you see maximum users IOs also, that is also 300 to 500. Okay. Now here also you can see that when I'm saying XE100T, so there is a lot of packagings, correct? So what we need to do, sometimes we select FPGA, and after that sometimes we feel that, okay, can I upgrade my system, because can I integrate a lot of users? So what exactly happens, you have to redesign all the system again. Okay, so that is again a problem for us. So for us, so what we do, so let's say you can see here FG484. So let's say XE100T, we having a 285 IOs there, correct? 285 IOs. And in 200T also, you will see at the last column where my cursor is there also 285 IOs were there, correct? Let's say you having a FPGA board which having 100T devices there, and you are running some application. Tomorrow you wanted to expand and make again a heavy algorithm, you wanted to put on that that board only. Okay, so instead of redesigning whole board, you simply, what you can do, you simply only change the 100T device with the 200T device. Because when I'm saying 285 FG484 and this FBG484, this also 285, so they are physically compatible each other. Means you don't have to be change the PCB layout, anything else. So you have to simply remove the 100T and you can simply put the 200T. Now what exactly happened, every design remains same, but the capability of the device is increasing kind of double. Okay, so again, when we making any kind of R&D, or when we making any kind of product development kind of thing, so we have to be look this kind of things also. Now, I'll give you one simple examples that how exactly FPGA now playing roles. Now in EVs, basically, for example, EVs. So now whatever the EVs you will see in the market, basically in India, basically I'm talking about the controllers, which is, we can say that ECU controllers. Okay, so that are basically DSP or kind of a microprocessor kind of controllers only there. Okay. Now people are looking a solution for FPGA, or that research is also going, even government also pushing towards this. So now here, what exactly, this is a simple block diagram kind of where exactly EV is kind of thing. So we having a power control unit, we having, you know, DC to DC converter, we having inverter motor control, we having battery management, there's a charger there, also we having AC to DC converter kind of thing, and this ECU. Okay, now what exactly happened, where exactly blue color you see conventional, if you see conventional control, so conventional control using DSP kind of controller over there. Okay, but now you can replace every control through the FPG. You can easily DC to DC control, you can do the FPG, inverter control, do the FPG. Now you'll see that what exactly the advantage of the FPG. If I replace existing or conventional control through FPG, what kind of things you will see. So we will see this kind of application. So now if you look into the current systems, we having this kind of system. So we having look DC to DC converter, we having motor inverter control. Sometime if you go for hybrid electrical vehicle, we having generator motor is there. Okay, so what exactly happened, for every DC to DC converter, I have a different PWM control and different master control unit is there. For this we having different master control unit, and this we having different master control unit. Second thing is this, that the conventional controller now you are using, the sampling rate is also very low. So basically when you're going to implement any PWM kind of application or kind of application, it cannot go very high. But now in coming days, what exactly happens, first of all, we are doing good towards the SiC based devices. Okay, today we'll know that SiC based devices are very costly, but coming days that will come down also, cost will come down also. So what is the big deal in the SiC devices? They can switch at very high rates. Okay, so for any drives control you go, these MOSFET SiC based devices can be, you know, can be switched very at very high frequency. This is the one advantage. So when I can switch SiC device very high, so what exactly happened, whatever the inductor, capacitor, or the passive things you will see, the size automatically reduce as I increase the switching frequency. So if you see inductor kind of thing or capacitor kind of thing, so automatically the size will impact. The second thing is this, in the current system in EVs, you will see that there is a 3 different control were there. The same control you can do on a single FPG basically. Why? Because FPG giving you a lot of IOs, lot of flexibility. So there is a lot of sensors that you can put on a single FPG IC. So basically the size and the things can be, can be reduced in a very good way. Okay. Again, the performance would be high, the performance can be high, and obviously it will save you the cost, because ultimately it again depend on the cost and everything again. Okay, second thing, FPG is again, we tell you that it is a parallel operation. So obviously when you go for any PWM, so it can give you a very high PWM kind of things also. It can switch, it can give you the sampling or the PWM up to megahertz also. Okay, again depend on the capabilities of the switching capability of the ADCs also, but FPGA having that kind of capabilities. Okay, so that's why even the government schemes, even the big players in the EVs also looking towards the FPGA solution, how we can make whole system on the FPGA kind of things. Why the need of customizations here? The first thing is that application specific. Now if you look into the domain of FPGA, so basically what exactly happened, for power converter applications we don't need Ethernet kind of things, we need only ADC DAC kind of things. So other things we doesn't require. Okay, so that's why we are doing customization. The necessary things which you required and which is important for you, this is what we are giving to you. Second thing is, it is a system optimized. For example, any applications where you need to run, for example, surveillance system you have to be make, or you have to be, video making processing you have to be make, or some kind of EV application you have to be make. Okay, so the customization of FPGA board we do according to that only, so that we optimize the system itself. We don't put a lot of peripheral. For example, EV kind of things, we don't need Ethernet kind of things. For example, I'm telling you, so we don't put that. We simply put ADC DAC. For example, if I need a communication kind of card, there we need a very high data transfer. So their ADC required very high kind of things. Ethernet, I need a Ethernet also. Some 485 communication protocol I need. So this kind of things we put. Okay, and with these systems, the efficiency, how we can improve the efficiency, how the size of the board can be reduced, and so that it can be directly fit into the kind of applications. Okay, now what the Vanix basically, what we doing, basically we targeting the different application. We target the electrical vehicle application, drives and control, multi-level inverters. Even we are targeting the defense application like electronic warfare, aviation technologies. Even we targeting the battery monitoring application, because today when we see that BMS, so there's a lot of parameter that we have to be sense. And when we say that lot of parameter that we have to be sense, means lot of sensors that you need, and all the sensor, if you wanted to want a robust control, and you wanted to put on a single PCB, so FPGA playing there also a big role. Even system connectivity and integration, this kind of applications we are targeting, and for these applications we making the FPGA boards. Now Vanix, the project what we did so far, so we make the board for power electronics kind of things. We made the board for the receiver interface board, receiver processing boards. We make the board for basically for OFC interface card also, BrahMos SG kind of boards. It's a different boards we already worked on. Now, some of the boards that I'll show you, these boards we basically worked and we delivered also. So this is the Vanix board for power electronics application. So if you look into this board here, we doesn't put any audio jack or video jack or VGA kind of things. Here we basically having 48 IOs. So you can see that here PMO 24 IOs, here 24 IOs, and these 48 IOs means all 48 IOs you can use for PWM application, because this board are for power electronics. So you can run any kind of application, multi-level inverter or kind of drives control where a lot of PWM required, or like say SRM kind of motors where you required a lot of PWM. So these are PWMs, you can use up to 48 PWMs. Here we also giving ADCs. These ADCs are 16-bit ADCs and 4 ADCs we put. So 16 sensors you can put on your system, and that whole sensors inputs you can give to the ADCs. Okay, again we having DAC, so sometimes we have to see our output also. So you need to be integrate the DAC separately. We have the 16 channel DAC also. So basically you can, obviously the capability of our oscilloscope should be there, but you having 16 channel together, you can see on a different oscilloscopes also. Again, one more thing that we thought that basically in power electronics device we required, we wanted a signals and signal conditioning circuit. So we given the bipolar signal conditioning circuit on the board itself. Means if you having AC signal, so you don't need to be do any programming or any signal conditioning. If it is a 10-volt signal, 5-volt signal or 3-volt signal, you can directly put into the ADC, and then you can program your FPGA accordingly. This Arctic chipset we used now, and this is the Arctic chipset. This is the highest Arctic chipset, 100T and 200T, both the chipset we used these things. Even we given the on base fault protection system. Sometimes what happened, there's a lot of things happened, and sometimes board become faulty. So this kind of protections also be given. Sometimes we need memory kind of things also, for let's say lookup table kind of things also. So for that also we given DDR3 memory. It is a 1 GB memory card also, so the DDR3, so that is also be provided. Okay, so this board basically we made for what? Power electronics application, where you don't need other application like VGA kind of things, or VGA sometimes we required for some things, but you don't need audio kind of things or video kind of things or HDMI kind of things, or RS230 type of protocols you don't need. You need a ADCs, high ADC numbers, high DAC numbers, high PWM numbers. Okay, so this kind of thing. So we made this kind of boards also. Okay, again we provide on-board bipolar signal conditioning on these things, and this board is proved. Okay, so what exactly this board is specifically fit into your prototyping kind of things. Okay, again based on the needs we can do the things in a different way. Again, if you look into the Vanix board, this is the PDC test. This is one project where exactly we required a different specification, RS232 Ethernet. They required a very high memory available. So this kind of requirement come, and then we made this kind of board, and that fulfilled this kind of. Even they give us the high speed frequency with impedance matched, where how the PCB should be. So we designed the PCB accordingly that. Okay, again we make one board, LNet board. Okay, it also having the specification like we need a 1000 Mbps Ethernet, we need a 1 GB DDR, we need a material. So this kind of things are required in defense kind of things. So we made a board kind of these things board also. And we having standard boards like this. We having a standard board like this also for different applications. Like if you wanted to research on EV applications, you can require this kind of board. If you need a this kind of board cater all the power electronics applications. Okay, for communication kind of things, we having a different boards. For audio and video or AI people who have wanted to work on the computer vision kind of applications, we having different kind of boards. So this kind of things what we doing. So this is all about us. Thank you so much. Thank you so much, all of you. If anyone having any questions, I'm open for that. Thank you.
Yeah, thank you very much, Rana.
Yeah.
So, dear friends, if you have any queries, feel free to ask to him on the topic. Yeah, I think Rana, I think it seems there is no queries. Thank you very much for your wonderful talk on the role of FPGA technology, its opportunities and future, and patience for spending your valuable time to present your work in our industrial sessions. Thank you very much once again.
Thank you very much.
Thank you. Yeah, thank you, Rana. Yeah.
Thank you very much.
Yeah.
Very interesting.
Thank you.
Yeah, Dr. Evgeny.
Yeah, Evgeny is here. Do you hear me well?
Yeah. Thank you, Dr. Evgeny. Shall we start your session now?
Yes, I can start and I should share my screen, right?
Yeah. Please give me 1 minute. Let me introduce you to our friends. Yeah. Good evening, everyone. We are going to begin our 4th industrial session. I would like to welcome Dr. Evgeny Janev. He is a CEO of EMPS Consulting LLC located in California, USA, who's going to deliver a session on electric engines for electric and hybrid aircraft. It is a great honor for me to introduce our speaker, Dr. Evgeny, of today's session. He is very well known for his work in the field of electric and hybrid electric aircrafts. Dr. Evgeny is the CEO of EMPS, Electromechanical Power Systems Consulting LLC. His main interest is in the electrification of the aerospace and automotive industries. He is focused on powertrain of electric and hybrid propulsion platforms. He has 40 years of engineering experience, 30 years of which with Honeywell Aerospace as a chief engineer for EMPS. His expertise includes power generation systems, electric drives, and electromechanical actuators, as well as aircraft and terrestrial vehicles architectures. His work materialized in platforms like F-22, F-35, International Space Stations, Space Shuttles, Predator B, Future Combat Systems, B-737, B-777, A-380, A-350, E-Taxi, A-320, and NZ-Jammer program for F-18. Numerous papers and speeches and more than 50 US active patents have been published. He is an active member of IEEE, IEEE, SAE, and ASTM. Evgeny has received many awards, including the SAE Charles Manley Memorial Award. Without wasting any time, now I would like to hand over the session to Dr. Evgeny Janev. Over to you, Dr. Evgeny Janev.
Okay, thank you very much for giving me this opportunity. And now I'm going to share the screen.
Yes, please. Yeah.
I do you see it?
Actually, it was earlier, it is visible, but now there is some problem. I think now we are unable to see our slides. Can you reset, Dr. Evgeny? Yeah, now we can see it.
Okay, so you now see my screen, right? The first chart.
Yes,
the
correct.
title chart.
Yes.
Okay.
Yes. Okay, thank you.
So what I'm going to present is electric engines for electric and hybrid aircraft. This is a tutorial which has been prepared jointly with Arif Salam, who is chief engineer at Honeywell International. Right, so Arif is on travel and he couldn't join the session. Sorry about that. Content, we are going to have introduction tutorial of the rules. What is electric engine for aircraft? Just because the diversity in this area is huge, we have more than 200 new startups and some big companies working in this area, so it makes sense to have some clarifications and definitions. What are the major definitions and terminology, right? That's something which the industry struggles to come up with common documentation and understanding. What are the power architectures? So the electric engines will be reviewed broadly in the lights of the electric craft architecture and also the powertrain. So then I'm going to introduce a high power propulsion burst, which we believe it's something which is quite beneficiary for implementations in the new electric and hybrid platforms, and then some results of trade studies, of course, the conclusion, and in the end we have a QA session. So welcome everybody to this tutorial. I believe hopefully it's going to be useful for all of us, and not only for the audience but also for me, just because as a part of these sessions I'm really collecting feedback from many engineers from all over the world, and it's useful for the entire industry. The main focus of the electric engine is for relatively small vehicles, kind of urban air mobility. Larger vehicles will be discussed as well. However, the focus is about this one kind of very fast developing area. Battery powered source will be considered, however, fuel cells are not going to be ignored. So the electric engines are really viewed in the light of vehicle architecture, right? And part of the power train. Interactive behavior is encouraged, of course, and the material will be delivered after the sessions upon request. The contact information is included here on the bottom and also in the end and the last chart. So whoever requests the material will be delivered as presented. This is kind of top level roadmap for implementation of the electric and hybrid vehicle. The trainer, recreational, commuter, conventional takeoff and landing kind of vehicles have been implemented for some time. And hello. Have been implemented for some time. And do you hear do you see my screen?
Yes, we can see it. Yes.
Yeah, okay, because something interrupted for a moment. So on the left-hand side, those vehicles are flying for several years. Some of those are already certified. These are predominantly two-seaters and sometimes up to 4. The biggest boom is actually in urban air mobility, where much complex vehicles have been designed and built, and there is a very big progress in regional aircraft, something like 10, 15, up to 20 seats, something which is already feasible as a electric and hybrid architecture. There is already a lot of activities in the narrow body for commercial aircraft. For instance, Department of Energy is helping the industry to develop technologies in this area. And then the second generation wide body is quite a question mark. Some experience needs to be accumulated in the small aircraft in order to target the largest aircraft. So overall incremental progress with technology advancement is expected. For the small vehicles and then larger vehicles will be included. Some more details on the bottom of each one of the classes are included about the power levels, about the voltages. Obviously, with the increasing of the size of the vehicle, the power levels and the voltages will grow in order to make it more optimized. What is the electric engine? As I said, there is I've been participating in many committees writing standards on the subject and many conferences. So in my opinion, there is no consensus what exactly is it, but here is an attempt to address this deficiency. Converts electrical power to mechanical power for electric and hybrid propulsion aircraft. It is part of any electric propulsion architecture, right? Regardless of what the source of power is. The source could be either battery or fuel cell. Most likely could be some other sources in the future for some kind of more sophisticated power generation system. The major components are electric rotating machine, motor controller, which is controlling the machine, and speed reducers in some architectures. Some are electric drives, right? Some people call it torque amplifier. And in most of the cases, this is a gearbox, although there are some other provisions which can be used for this purpose. It has to be FAA or EASA certified or some other authority, the same way like gas turbine engine, and this is to part 33. It is safety critical component, DAL level A. Redundancy is quite frequently required when it's on engine level or let's say higher aircraft level. So in general, electric engine plus thruster is what replaces the gas turbine engine in the electric propulsion. However, we will see a little bit later, it's not always the case. Engine typical load, just because of the nature of the load, the curves are as seen. At takeoff, it operates typically 80% of the rated power level, and it has 20% reserve in case of some dynamics needs to be compensated. In cruise, it's typically around 40%. So this is typical behavior of the load, power, and also torque, delivered torque. Three major components are included. As I said, electric motor is a must, and the motor controller definitely is required, just because the motor is always brushless. Doesn't make sense to use some old brush type of technology, and this is the minimal configuration. However, in most of the cases, especially at higher power level, and it depends on the thruster as well, right? A torque amplifier is required to gearbox. Highly integrated system is highly desirable, just because when you share a common chassis, common lubrication system, common cooling system, this is the most competitive design. This is the smallest, lightest, and also the cheapest electric engine, just because as a part of this heavy integration, less material is used in smaller number of parts. Although distributed, let's say, separate motor controller is doable, and in some architecture it probably makes sense to have it, but overall for higher powers level, above 100 kilowatt, 200 and up kilowatt, it's highly desirable to be integrated. What are the major definitions and terminology? So this chart depicts the several major components. The minimal configuration, as I mentioned already, is the motor controller and motor, and in the shaft of the motor, the propulsor can be connected. A typical configuration is when there is a gearbox, as I said, especially when the power levels are high, and after the gearbox, the propulsor is included in these applications. The speed is anywhere between 1 and 2 kRPM, so definitely gearbox is required. And the maximal configuration is when the propulsor is part of the engine. So we have at least 3 how to say top level definitions of what engine is and what and what kind of components are included. In maximum configuration, propulsor is heavy integrated with the engine, like if it's a ducted fan, which means this is pretty much one LRU and one assembly, and it needs to be certified as a integral part of the propulsor. In other cases, when the engine is lesser configuration, the propulsor is typically certified as a part of the aircraft or separately. Definitions and terminology. Powertrain, it's clear, it's something which is used for used in the automotive industry as well. Electric engine, until recently, let's say about a year and a half ago, electric propulsion unit used to be used instead of electric engine. However, EASA jointly with FAA decided that they need a term which is much closer to the classic engine term, and they suggested us to change it to electric engine, and now we are in process of changing this term and some other terminology to fit much better for certification purposes. And I'm talking about the standards of SCE, some other organizations. Motor is electric rotating machine. Motor controller is inverter plus the signal portion of the motor controller, and gearbox, the third component. So these terms are kind of widely used in these different committees that we are putting together standards. We have ambassadors, people which are participating in more than one committee, not only in one organization, but different organizations. So we are trying to transfer and unify the terminology across the entire industry. Just because, how to say, to be honest, since people from all over the world participate in these events, the fair amount of time is spared to understand each other. What are we talking about? So the biggest troubles are related to the terminology. Once the terminology is clarified, things move much faster. Electric bus, AC or DC, high power propulsion bus, and then the system and subsystems of the powertrain, electric power generation system, electrical power distribution, electrical energy storage. So these are typical of course, complete definitions are included in our documents. What are the powertrain architectures using electric engine? So this is what NASA came up with architecture. Initially, they defined 4 architectures, then expanded to 6, and we different organizations and committees adopted this approach in order to do this across the entire industry. So I'm not going to dwell a lot on these architectures, but it's obvious that the common thinking is each one has electric engine. The ultimate goal, of course, is to go to all electric, battery plus electric engines. Obviously, this is the simplest architecture, the simplest system possible. This is the cleanest, and over the time, it's going to become the lowest cost architecture whenever the batteries become more affordable and more reliable And initially, small vehicles are doable with this architecture. However, all other architectures are possible, and it will be transitional technology for small vehicles for short period of time, 5-10 years to 15, for larger vehicles for longer period of time. So these are the 6 basic architectures. However, many possible derivatives are possible depending on the parameters and requirements of the vehicle. So in this line, extensive trade studies are required to be able to come up with the right architecture. Just a moment, something is happening. Yeah, so extensive, we are in possession of tools which are very helpful in coming up with the right architecture for certain application, for certain mission profile and vehicle requirements. And here is kind of a summary of the major components of those architecture. It's obvious that only 2 architectures do not have batteries. And these 2 architectures may be either AC or DC distribution buses. Once we have a major battery, large battery as a part of the power train, then it makes sense to be DC bus. AC to DC multiple conversions is not desirable. And here we have several questions related to the architecture, which may inspire some of us right to think about this, to have a discussion. However, as a part of this presentation, it's too short in order to go to the questions, and I really encourage material will be distributed, and whoever is interested just to give an answer of these questions, and we can get into discussion, email, or we can establish some kind of longer term contact, but I'm willing to support continuation of this effort. What are the major architectures and components as a part of the electric engine, right? So until now we talk about the next level, the powertrain architecture, but now we are going to get internally into the electric engine, right? So first of all, as a part of coming up with the right engine, again, extensive architectural studies are required internally. So several electric machines are the winners typically. Induction switch reluctance and radial air gap machine are left outside, although some kind of exceptions are possible. And some kind of exceptions are quite possible. And there is something going on. Something is. Do you see my screen now?
Yes, Dr. Ravijani. Yes, but not PPT. Like your mail is got open. Yes, now we can see your PPT. Yep.
Yeah. Okay. So evaluation of the speed is required, right? How fast the electric machine is going to work. It's clear that the faster machine, the higher speed is coming up a better way, just because the machine is sized by the torque. It's a smaller machine, so several different speeds can be evaluated. Materials for the different components needs to be well understood. So 3 machines are very good candidates for electric engine. Permanent magnet surface kind of machine, Hallback array machine, and interior permanent magnet machine are preferred machines. The rest of the machines have worse performance, and also they have some other deficiencies. And this is the cross section of these three different machines: surface permanent magnet, holdback, and interior permanent magnet. Interior permanent magnet dominates in the automotive industry. However, for relatively small speed application is also a very useful machine. The other major component is the power electronics. Two major components, two major architectures are highly desirable: three-phase bridge and three-phase bridge with a booster. With the booster, the simplest top one is typically the winner, but in some vehicles and some mission profiles, the second one with boosting schematic works. Let's say topology configurations with multi-level, three-level inverters and higher level, it may help in reducing the losses, and also it may help when availability, when we're dealing with very high voltage, and high voltage devices like silicon carbide are not available for these voltages and power levels. And let's say resonant converters, there is attempt to get in use. However, it's not very promising at this point, but doesn't have to be ruled out. And some components, the key is the silicon carbide high voltage devices, high power with enough current. Paralleling of many of those devices is going on. The automotive industry is moving towards this direction. And the other important element is digital signal processor control. But of course, FPGA can be used instead of software related, but these are the two important technologies that comprise the power electronics. The gearbox or torque amplifier or speed reducer, these are typical arrangements per gear for a low speed up to 12-15 kRPM can be used. However, when we go to 20-30 kRPM, a planetary gear is required, and in some cases even 2 stages. So for these power levels, let's say to 250 kilowatt applications, about 60 kRPM is kind of maximum speed that can be achieved in an electric engine, the motor of the electric engine. And the architecture, a little bit more details about what is inside of the electronics, the permanent magnet machine, and also the speed reducer on the right hand side. Again, I'm highlighting that the best results are achieved when the system is heavily integrated. And system selection from how to say mechanical arrangement. On the top we see an option which is with a 2 planetary gears, so the motor and the output shaft of the engines are coaxial, and it's really something with minimal package. However, when spur gear is used, which is a cheaper solution, we have a gearbox offset, and in some installation this is not desirable, but in some may be beneficial. So again, highlighting highly integrated system and high-speed electric machine is best for high performance. And here again, I have questions to these sections, and we're gonna pass it just because the interaction will be very difficult and time consuming. However, afterwards we can always go back and really interested to support with any one of you. Introduction to high power propulsion bus. So this is something which I came up with this idea a few years ago, and it came from the fact that if we follow the same rules of VMI and power quality, we are going to come up same rules what's been established in the industry. we are going to come up with very heavy system. This is why we need to do something special. So create a dedicated DC high power propulsion bus, right, with reduced TMI and power quality requirements. And this is applicable for the powertrain. Includes all components and interfaces in Faraday cage, right? Just because many of those are sensitive to interference, and also the very system emits a lot of electromagnetic noise. Eliminate inductor-based EMI filters in all the components, just because those are the heaviest components, and those are really energy consuming, right? So inverters should be assisted by the battery capacitance. So it would be nice the battery to be as close as possible to the electric engine. In some architecture it's easy, in some it's difficult. Use high voltage battery for reduced system current. This is where the battery technology is moving. If generator is used on the same bus, it's easy to control the generator to follow the battery voltage. So the battery voltage varies based on the state of charge and mode of operation, either charging or discharging. So this is something which is easy to control if we need parallel buses with the two sources, no matter what the technology is. And keep separate regulated DC buses for the smaller loads. And EMI power compliant for utility loads and flight control actuators can be kept as is. So what is the advantage? Since these are spread throughout the entire aircraft, it would be nice to be compliant. These are small power and they don't ruin the overall aircraft performance. And also a lot of hardware from the past already developed can be reused. So on the top side is the powertrain architecture of aircraft using high power propulsion bus. So everything which is electric hardware is shielded. On the bottom portion, we have DC to DC converter, EMI filter, and the rest of the low power loads are really compliant. So this is an idea which I believe roughly can save about 20 to 25% of the load of the powertrain compared to if it would be designed per the well-known classic EMI and power quality requirements. Major trade studies to obtain optimized system. Again, as I said, typically when a new system is starting, extensive trade studies required, and this is applicable even more when we are talking about electric and hybrid propulsion, just because no matter what kind of vehicle is it, it's something new, it's something which never existed, nothing similar, right? So there is no experience to step on it, and as a result, extensive trade studies are required prior to making commitment to build and test hardware. So the main objective of those studies is to define the optimal mechanical architecture. For instance, is this direct drive versus gearbox based system. Selection of the electric machine is definitely important part, and the trade studies should be on aircraft level, electric engine plus the powertrain architecture plus aircraft. So the mission profile needs to be included depending for the same aircraft, depending on a typical mission profile, you can go one way or another, different electric machines, for instance. To define the optimal motor speed and the gear arrangement, define power topology and the control methodology, mechanical package of the three major components. As we mentioned, it's very important. Materials, components, the cooling scheme, and lubrication scheme. Right. Sometimes those are given by preference from the vehicle level. However, upon opportunity to have substantial savings, those can be changed. Right. So broad trade study required to select optimal system. And now I'm going to go through. So the nature of the load is shown on the right-hand side. We're going to study, show the results of a system which is 200 kilowatt max power. The torque and the output speed, max speed is 1.2 kpm, 1600 Newton meter. Delivered torque, input voltage, actually it applies up to 800 volt DC. And the major component is the speed. So several different speeds will be studied in order to see what is the sensitivity from speed perspective to the performance of the electric engine. So when we start these trade studies, we have to establish firm critical to quality items. So these can be different elements like performance elements like weight, efficiency, volume, reliability, cost. Here is given an example. Although these critical to quality items are with different units, there are algorithms, iterative algorithms developed to come up with optimized system. All of these parameters are not directly comparable. Electric machine selection and design, we talked about this. So here, surface permanent magnet machine has been selected, and also interior permanent magnet machine can be used for lower speed. So we said the 12 kRPM is one of the speeds, but we studied 1.2 kRPM, which is actually direct drive without gearbox, because the output speed of the engine is required to be reached. So for 1.2, 4.2, and 12 interior permanent magnet machine can be used. Performance-wise, will be very close to surface machine, and the cost may be lower, right? However, for the higher speeds above 30 kRPM, the interior permanent magnet machine doesn't make sense, just because the tip speed of the rotor is limited. It can be improved. However, it makes the machine not that competitive. It gets much heavier. Again, here we are talking about these two possible topologies. It depends on the specific application. And for the mechanical architecture, it's shown higher speed above 30 kRPM. You definitely need a planetary gear. And we talked already about this mechanical arrangement. So an option which wasn't shown on the schematics before is to have two planetary gears. So one after another, which makes it with better performance overall. However, it's more expensive. And again, I'm highlighting that highly integrated system is highly desirable for best performance. And results weight. It's obvious that the electric machine, which is the top blue, is getting bigger and bigger just because the size is highly dependent on the torque. And the same power with larger torque is larger machine. Of course, the speed is smaller, the gearbox is getting smaller, and at the end it's zero, right? Just because it's direct drive. However, overall, if you look at the bottom chart, the weight starts increasing quite drastically when we are going towards direct drive. water speed. The biggest improvement is from direct drive to 30 kpm. Then the improvement declines. However, it's still quite substantial. So for this application, it's clear that the high speed is the most beneficial. And when we are talking about weight, it's not the weight on itself, but there are other benefits which are desirable too. Then we are talking about efficiency. The controller is considered to be equally efficient for each one of the applications. Of course, the gearbox efficiency is best when the gear ratio is smaller and the direct drive is 100% just because it doesn't exist. On the bottom, overall efficiency is getting better when it's direct drive and low speed because of obvious reason. However, the good news is that better than 90% of efficiency is achievable for any one of the options. Then we are talking about volume, which is similar to the weight. However, the volume is having a little bit more complex chart for the total, which is the ratio between the overall mechanical components and the volume of the machine and many other components. So this mechanical volume has a strange behavior, primarily because of the size of the housing and other mechanical components. Then reliability, these are in relative terms. The motor controller is equally reliable, the same number of components, pretty much the same size. So the reliability of various components is depicted over here, and so it needs to be part of overall consideration, and definitely mechanical components benefit from the lower speed overall, and it's slightly better reliability when the speed goes down. Cost, this is in relative terms. Again, the motor control is adopted as unity. Machine costs strangely increased when the speed decreases just because of the cost of the material. It's larger machine. Other than that, it's, let's say, very similar. The higher speed doesn't come from some exotic technology. It's primarily ability to integrate with other mechanical components and to integrate and control it electrically and mechanically, of course, to control it. So this is why the low speed system seems to be looks much more expensive. Then results. This is summary template chart which compares various critical to quality for the 5 selected different speeds. So at the first glance, the dark color, dark green is best, lighter is worse. So someone could select the high speed. However, in some applications where the efficiency and reliability are very, very important, then direct drive can be selected. For some application, let's say 30 kpm may be acceptable. Again, next level of understanding and the mission profile is required in order to say, okay, this is the speed, what is highly desirable. Trade study results. So we went through those important critical to quality. However, some other important items needs to be considered as well. For instance, audio noise. In typical aerospace application until recently, when you always have conventional engine, either for auxiliary power unit or main engine or whatever, it's so noisy that nobody cared about gearbox noise. Electric machine electronics are easy to make low noise. However, gearbox are problematic, so it needs to be considered. This is one of the major obstacles. Depends if it's electric only, everybody enjoying very quiet vehicle. If it's a hybrid and there is constantly operating conventional engine as a source of power or propulsion purposes, then the noise is not that important, but it needs to be considered anyway. Maintainability is very important. Yeah, just yeah. Hello?
Hello.
Yeah, do you see my screen?
Yes, we can see that. Yeah.
Yeah, so sorry about that. Maintainability, safety, very important. It needs to be separately evaluated on aircraft level. As a separate thing, certification, it must be certifiable, right? So, and the system inertia is also something important when the engine is used as a highly dynamic engine and needs to modify the speed very, very quickly. So this is really something which, in addition, needs to be considered, needs to be addressed, and then the inertia can be managed more or less with the aspect ratio of the rotor and ability to integrate the electric machine with the mechanical loads. Summary, conclusion. Extensive qualitative analysis needs to be performed. System components and design needs to be performed. Results may vary depending on the specific platform requirements. You mentioned that certification may influence some of the results and you need to go back and to change to redesign. High-speed geared electric machine options present the best overall performance. Some low-power applications, the direct drive, not yet may be preferred, and overall heavy integration and high-speed motor options are recommended for best performance. However, we don't have to rule out the other options just because in some cases they may be more desirable. And conclusions. Conclusions and opportunity for improvement of electric engine. It should be adapted to the powertrain architecture to extract value. So here this high power propulsion bus needs to be definitely considered, right? And it needs to be designed, in such a way that the entire powertrain is optimized, not only electric engine by itself. Electric engine design should benefit from battery capacitance. Something like this has been understood already and implemented in some electric passenger vehicles where the conditions are much, easier to achieve. A passenger vehicle is typically much smaller than any of the aircraft. The distribution of the components can be such that the battery and the engine are very close. Typically, it's only one electric traction drive system and one battery. So it's much simpler problem statement. And this is quite encouraging just because this Faraday gauge and high propulsion bus. The bus is very short. That's the bottom line, right? So similar approaches can be used in aerospace. Different power quality and electromagnetic compliance should be created in order to satisfy the implementation of such a bus. Uncertainty and reliability should not be a major obstacle. In these committees where we discuss certification with the authority, FAA and EASA, one of the biggest concerns is reliability. So in my opinion, we should not overreact in this area just because from common knowledge, let's say authorities are nervous just because they start dealing with unknown hardware and unknown behavior of this hardware. But just to compare several items, for instance, the temperatures, conventional engines operate at thousands of degrees Celsius. Temperatures here, we can rarely go to 110, 120 degree C temperatures in electric machine or in electronics. So the thermal stresses are minimal. The number of components and the connection between these connections is much smaller compared to conventional engines, and this one improves reliability. It's only a matter of how to say more test results in order to see where we are. Thermal management of large system is still very challenging, and it needs quite a creativity. Certification is lagging the industry demand, right? There is pressure to authority to do it faster. However, they are very nervous just because the standards are not ready yet to step on it, not enough experience, not enough flight hours in order to come up with a meaningful certification process. Infrastructure development needs acceleration. The same is seen in automotive industry, right? So the mayors of the cities, the large cities, are reacting very, very slowly. One day these vehicles will be designed, developed, and certified. However, without infrastructure in the cities or dedicated airports, it's not going to be progressing as fast as society requires. One element, artificial intelligence, will boost the introduction in pretty much every aspect during the entire design process, implementation process, service. So artificial intelligence is going to play very, very important role. Also, autonomous vehicle implementation is important. It doesn't belong to this kind of presentation and short course, but we don't have to be ruled out. So everything needs to be looked from the aspect of the big picture. So electric engine progress benefits from steady electrification process in the aerospace. It's definitely becoming much better compared to the previous designs and ideas are. So there is, like in the automotive industry, there is no way back. The massive electrification is not a question, is it going to happen or not, but this is when, and as we look in the beginning, it's going to have different time frames for different sizes and different vehicles. And this is pretty much everything what I have to say today. And thank you very much for attending this session. As I said, material will be delivered upon request. So I show two emails over here. When I receive a request, material will be distributed. So future communications we are going to have upon your interest. And now we have a few minutes more for questions, which I should be able to address as a part of this presentation. So I'm waiting your response now.
Yeah, thank you very much, Dr. Evgeny. Dear friends, if you have any queries, feel free to ask to Dr. Evgeny Janev. Dear friends, if you have any queries on this topic, feel free to ask to Dr. Evgeny.
Okay.
Okay, Dr.
Any
Evgeny, I
questions?
think, I think it seems there is no queries on this talk. Thank you very much for our wonderful talk on electric engines for electric and hybrid electric aircraft, and patience thank you very much for spending your valuable time. I hope all our participants have gained a lot of information, and I'm sure that your session is very helpful for most of our participants who's working on this area. Once again, I'm very much thankful to you for spending your valuable time to deliver this session. Thank you very much, Dr. Evgeny.
Yeah, thank you. Thank you very much to you too for giving me this opportunity. And as I said, I'll be always open to support the audience for some other future events. Thanks again.
Thank you. Thank you. Thank you very much. Have a great day. A great day. See you. Yeah. Thank you. Dr. Evgeny, I think you can stop sharing and yeah.
Yeah, I'll do it.
Yeah. Thank you, Dr. Evgeny. Yeah.
Yeah, I did it. Thanks.
Yeah. Thank you.
The recording has stopped.
Yeah, thank you very much, friends. This is for the day. This is the last session. Thank you very much for spending your valuable time to attend all the sessions, including tutorials and investor sessions. And see you tomorrow at the inaugural session. Thank you very much. Have a great day. Thank you.
Okay, thank you very much. Thanks.
Yeah, thanks, Dr. Evgeny.